in the previous lecture we proved Wick's theorem, but so if you look at any standard textbook in quantum field theory, so Wick's theorem is usually done for time ordered correlators. Time ordered correlators. I will explain what this is. But we didn't assume any such thing, okay? So now I will relate it to the thing that is usually done in most textbooks. So first let's try to see what is time ordering. So time ordered operator this is defined to be theta function t1 minus t2, so t1 is greater than t2, phi t1 phi t2 plus theta function t2 minus t1 . Okay, so this is the definition of time ordering. In the same way, let's say you have time ordered product of three operators. Then basically it is something like theta of t1 minus t2, theta of t2 minus t3, plus other permutations. Now it is clear from the definition that the time ordered product is related to somehow. So if I let's say if I want to take its expectation value somehow, something like if I let's say, okay, let me write here. So vacuum expectation value of time ordered operators can simply be written in terms of Feynman operators, Feynman functions. Okay, so let's first see how the thing modifies. So Wick's theorem for time ordered operator. Okay, so in the Wick's theorem, then Wick's theorem for Wick's theorem. So we remember that in case of Wick's theorem, we had some set of operators. And we written it in terms of completely normal ordered plus contractions, all possible contractions. The thing is that if you now put time ordering here, then this becomes time ordered, and then the contraction in that case, so contraction of this just follows from the definition, this contraction rule. So Whiteman propagator is replaced by Whiteman propagator is replaced by Feynman propagator. Okay, so then basically the thing is that for time ordered so the thing is that if we want to use Wick's theorem for time ordered operators, then Whiteman propagator will be replaced by Feynman propagator. Okay, so this is the only change. Other than that, it remains it remains fine. I mean, it remains the same as the other. I mean, the algebraically the structure theorem suggests you have to replace the Whiteman propagator by Feynman propagator. So now, from now on, we will restrict to time ordered product of operators only. And this is our assumption. This actually comes from I mean the reason behind this assumption will come later. So at this point just assume it, okay? And so then what we are interested in, so our goal is to compute vacuum expectation value of such things, okay? So now we have already proved in one of the previous lectures that vacuum expectation value of an operator of a normal ordered operator is 0 unless it is proportional to identity. Okay, so which means that if I now do Wick contraction for this, if I now just use Wick theorem for this, then only the fully contracted puppies will contribute. Okay. So let's see and how do you do that. So let's say we have 4 operators. Let's just do this. T3. Then by Wick's theorem, this is same as this plus single contractions something like this, I mean plus other permutations plus double contractions. Plus of course permutations. Now you see one important thing, that since this operator is not proportional to identity, this is simply 0. Okay, this is normal order, and expectation value of any normal ordered operator between vacuum is 0. This part is also not proportional to identity because 2 of them are contracted, but there are 2 remaining operators, so this is also 0. So the only non-zero answer comes from here. I mean all 2 contractions. Okay, which means that in this case the answer will be simply so this if I contract 1 and 3, this will be d1 minus 3 d2 minus d4 plus df. So 1 and 3 I have contracted, 1 and 2 I can do, 3 and 4, and then of course 1 and 4 and 2 and 3. Okay, so this is the final answer, and there is a beautiful diagrammatic way to do that. Diagrammatic way. So diagrammatic way is that for every point, for every operator you draw a point. So we have 4 operators, we have 4 points. So let's say this is phi of t1, phi of t2, phi of t3, phi of t4. Then the first line, okay, let me use some colors. So the first line we can draw. So this is, since this is a propagator between 1 and 3, we draw a diagram like this: 1 and 3 and 2 and 4. Okay, the second one, the second piece, for the second piece we again draw, let's say 1, 2, 3, 4. The second piece is just 1 and 2 and 3 and 4. So this is phi of t1, phi of t2, phi of t4, phi of t3, and then you have third one, and so this is the third one. So this is just have propagator between 1 and 4, so 1 and 4, 2 and 3. 4, 2 and 3. Okay, so you see that this vacuum expectation value of a time ordered product of time ordered operators. This has a nice diagrammatic expression, and the diagrammatic expression basically starts from 2-point function. So let's say start from 2-point function. So we know that this is simply the Feynman propagator, and this is usually drawn as you draw 2 points and you connect them. Okay, so this thing is the diagram. Actually, these are called Feynman diagrams. Okay, so later we will see that, so up to this point what we have done. So what we have done is that first we considered time ordered product of operators. Second is that we used Wick's theorem to write it in terms of Feynman propagators. Third step, if we want to take the vacuum expectation value, then only the fully contracted piece contribute. Only the fully contracted piece of Wick theorem contribute. Okay, and of course we have to do all possible permutation. We have to contract in all possible ways. And fourth is that every such term of Wick theorem of vacuum expectation value we drew a diagram. Okay, so in the next lecture you will see that we will start from this step. We'll start from time ordered product, but then we'll directly go to 4. Okay, and this technique was actually invented by Feynman to how to do this computation using just diagrams without doing the algebra, and this gives a very nice way to compute to do the computations in quantum field theory just using diagrams. So not only these diagrams provide you a computational tool, sometimes it also gives you the intuitive picture. And originally Feynman just invented those diagrams using using his intuitions. Only much later they were put in rigorous computational footing by Dyson in 1950. Okay, so we will see in the next lecture that how to do all these computations like time ordered product, Wick's theorem, all of them we have developed by this point, and we have used them to draw the diagrams. But from future lectures we will see that we will just draw the diagrams to do the computations. Okay.